All right, we're back for day 17 of Advent of Code. Here we go. Ooh, instruction pointers. Ooh, a program. This will be fun. Oh boy. Determine what the program is trying to output. Do this, initialize the registers, then run the given program, collecting any output produced by out instructions. This program is very small. That's curious. Okay, well, either way. So what we're going to have here, 3 registers. So I guess we'll start by doing this. Get the 2 segments. And then regs of, let's do this, -1. Let's go to nums of reg. Get the first number. Okay, cool. So that initializes the registers. And then this is just going to be nums of L2, I think. Okay, 8 instructions. Is it worth even implementing all this logic to figure out what it's doing? It must be. Okay, I'll just like work through this as I go and not worry about what it's actually doing. Run the given program, collecting any output produced by output instructions. Yeah, okay. All right, sure. So here's what we'll do. Instruction pointer starts at 0, pointing to the first 3-bit number of the program. These are all 3-bit numbers, the program. So we'll just do this. Instruction is going to be prog IP. If the instruction is 0, the A register raising 2 to the power of a combo operand. I should read this more carefully to figure out what's going on here. Instruction pointer increases by 2 after each instruction is processed. 8 instructions. And then there's an operand. Okay, so instruction operand. Great. Except for jump instructions, it increases by 2 after each instruction is processed. Okay, we'll worry about that later. If it tries to read an opcode past the end of the program, it instead halts. Cool, easy. Technically, read an opcode. Okay, technically the last one could be a jump, that's fine. Okay. Value of a literal operand is the value itself. Combo operand. Represent literal values. Combo 4 is A. Okay. Let's write a resolve combo. Do that. Just good to add some handling for that so that we find out if we wrote a bug. Cool. Oh, it's a combo operand. Okay. Division, numerator. Cool. So num is going to be this. And then the denominator is going to be 2 to the power of the combo operand. So that's going to be resolve combo of operand, I think. And then what we do, result of the division operation is truncated to an integer and written to the A register. Okay. Bitwise XOR. Okay. Stores the result in register B. To literal. Value of its combo operand modulo 8. writes to the B register. Jump not 0, okay. Does nothing if the A register is 0. Else jumps by setting the instruction pointer to the value of its literal operand. Not increased by 2 after this instruction. Okay, cool. I already did the increment here, so this is just completely fine. To the value of its literal operand. Okay, that's actually just going to be this. Bitwise XOR of B and C reads an operand but ignores it. What does this mean? Oh, gotcha. An operand. Okay. I bet that'll change in part 2. Stores it in B. Could have written that a little bit better, but an out instruction, value of its combo operand modulo 8, and outputs that value. Okay. Great. Except that the results stored in the B register. Numerator is still read from the A register. C register. Cool. Okay, I think that's fine. Final output of this. Okay. This should be IP. Instruction pointer. Okay, that's not great. Reg. Do I just have an input parsing bug? I do. What am I doing here? Oh, whoops, I'm assigning. Oh, no. Oh, I see. Reg of reg.find. Whoopsies. Okay, cool. I got an output. What does it want to do? Use commas to join. All right. I don't know if that's right or not, but I'll try it. Rank 228. Okay, cool. Lowest positive initial value for register A that causes the program to output a copy of itself. Oh, boy. This is going to be lots of fun stuff. Okay. This value is corrupted. This will be interesting. Let's put this whole thing in a loop. Sim for some starting value of A. And this will be initial registers. And then what we'll do bad way to write iregs.copy. Then we'll just return the outs. Now it's possible we infinite loop. It's also possible we should just be understanding what's going on. I have a good guess already of what it's doing, and that's probably like reading this as a base 8 integer or something, and then outputting all of those. That's my guess. I will make some attempt at doing that in a second. This should not have been indented. What did I do here? I indented way too much stuff, didn't I? Okay, I don't think I need this anymore. Cool. So now we just have the function. So if we sim for the value we started with, what does it output? Nothing, because I messed up. It's defined right here. What's the problem? Return. This needs to have some context. That'll work. It's not great, but it'll work. Sim. Same answer as before. Yep. Okay, and then let's just check if we add 1 to this. Yep, what do you know? That changes by exactly 1. So I bet if we do this, what does the number look like in hex? Hex is actually not quite right. But I think we have the general idea of this here. I bet if we add another 0, does that like do some stuff? Or technically not add another 0 times 8. Does that just add a 0 to the end somewhere? Sort of. It turned this 7 into a 1 and a 6. That's curious. I guess what we can do is, can we just actually like straightforwardly binary search this? It's sort of unclear to me. Like if it is truly doing some variation of what I said, then yes. Okay, so what did I do here? Times another 8. It's definitely doing something similar to what I said, but not exactly. I wonder if it's doing it in base 9 or something and using the extra bit for nothing. No, that doesn't seem right. Well, in any case, adding 1 does what to it? Adding 1 adds 1 there. If I add another 1, then do I see 0, 2? No, I see 4, 1. Oh, it's because the XOR. I bet it's XORing each individual chunk with something. Well, anyways, let's like take a crack at this. So what's the length of the thing that we care about? Let's start by getting in the ballpark of that. Well, if that isn't indicative of something. Okay, so let's do. Cool, seems reasonable. And then the target is going to be the program. Backwards. Thinking about it backwards is just a little bit nicer, because now, we already knew that. Subtracts 1 from the end here. Oh wait, no, we need this to be longer. Oh, I counted the number of commas. Yeah, that was kind of trolling, but okay, let's see what we can do. If we take this, we're just trying to make the last. Let's do this. What the? I should have just looked at this from the beginning. This looks like it's counting in some like XOR order. So let me make sure it's the same for every digit. 5, 7, 6, 1, 0, 3, 2, 1. Why does it repeat? That's not great. 5, 7, 6, 1, 0, 5, 7, 6, 1, 0, 3. Okay, this does look pretty promising for just like some counting order here. What does it look like within one of these? 1, 5, 4, 0, 1, 1, 3, 2. I'm not able to get 7s or 6s from this sequence, but I got them here. Is it worth just understanding what it's doing? How does the leaderboard look right now? Nobody's gotten a star yet. Should I just understand what it's doing? I should probably just understand what it's doing. Oh, but I'm like, this feels like it could lead to something good. But I should probably understand what it's doing. So let's do that. Here's the code. So hopefully it always stays aligned. So maybe I'll divide it like this for starters. Oops. If I find out it's not aligned later, I'm going to be incredibly sad. Okay. I'm adding the instruction counters so I can figure out where the jumps happen. Okay, cool. So what is the very first thing that it does? So where's the output? The out is opcode 5, so that happens here. And what is it outputting? Combo operand modulo 8. So it's combo operand. The operand here is 5. 5 is register B. So this is basically like print B. Print B mod 8. So that's what this bit is doing. I should really just add a lot of spaces here so I could like actually work like with a real scratch pad here. Cool. And then let's go back to the beginning. 2, 4. So what is this doing? This is doing combo to B. Maybe I should read it like this: B to combo 4, which is A. 1, 1. That is BXL. So XOR B store the result in B. B XOR the literal operand, which is 1. 7, 5. That is divide and store in the C register. Divide by 5. It's a combo operand. So 5 is B. So, okay. Store in C. I'm just going to label these. I'm like translating this to something that I can kind of roughly read. Okay, 7, 5. CDV. C divide, store in C the result from the numerator from A. So A, floor, divide by 2 to the combo operator, I believe it was. Yes, combo operand, which is 5, so B. Great. 0, 3. This is A divide. A over 2 to the 3. 3 is a literal value, so this is 8. When it's a combo operand. 0, 8 is 1, 4, 1, 4, BXL, bitwise XOR, store resultant register B. So bitwise XOR with the literal operand, which is 4. And 10 is 4, 0. 4, 0 is bitwise XOR B and C and stores the result in B. Ignores the 0. B and C stores the result in B. Yep. Okay. 12 is going to be output B, mod 8. And then 14 should just jump, not 0. Yep. So jump to setting the instruction pointer to the beginning. Oh, so that's 0. Jump not 0. A to beginning. Okay, so now this is workable. B and C start at 0. So what's going on here? First, we stuff it in B, then we XOR with 1, then we divide by 2 to the B. This feels very odd. Let me sanity check this again. 7, 5. C divide. Result is stored in the C register. The numerator is still read from the A register. Okay. 2 to the B. What is the C register used for? It's used for XORing B. So B is the output. Maybe we should trace that back. Oh, I sort of see. This is a little weird. Wait, no, 2 to the B is just weird, right? I guess I'm gonna add some prints. And then let me actually do sim with my number, the first number, which is this one. Okay, so is that doing what I think it's doing? Oh, it's BX. Oh no, wait, 0, 0. We're supposed to do what? 2, 4, 2, 4, BST. Value of the combo operand. Oh, modulo 8. Ah, I missed that. God, okay, this makes way more sense now. Okay, so grab the bottom 3 bits of B, XOR with 1, and then that is how, like, which chunk of A to extract. So we're like taking out this C, and then we're using it to ew. This is really weird. Has anyone solved yet? Still no one. Oh, one person solved. Wow. Oh, they're gonna start flooding in now. I better figure this out. This almost feels like I want like a SAT solver or something. Like it feels like there's a non-trivial dependence between different parts of the input, and it's not doing trivially the thing that I said it was. Maybe it is. The deal is that we're taking the bottom 3 bits of A, XORing with 1, and that tells us where to look in A to extract a C. And then we... So B is ultimately the thing that gets written out, I guess. This is just such a weird process, and it's not clear to me how to begin to approach this. But I guess okay. So the first thing we need to do, let's think about the output that we want to create. We want to create this. So 2 is the first thing that needs to get outputted. So first I'll be outputting 2 here. That means that at this point, B XOR C is 2, which means that problem is C is sort of like a non-trivial dependence here. What is clear is that A should be seen as blocks of ultimately what's happening with A in every iteration. A is like we're lopping off the last 3 bits in every iteration. We sort of start with the last 3 bits and then we do some sort of like messing with them. That's why A is shrinking like this. The messing with it that we do comes from C. And all that really matters is the bottom 3 bits of C because we're doing the XOR and then we're outputting modulo. So I sort of see what's going on here. Yeah, I guess there's a few possibilities for the A here. That tells us where to look later. I think at some point, B will just be telling us to look pretty far past A. No, the C is kind of always doing some mucking with things. How's this doing? A few. I really don't want to use a constraint solver here. I'd really like to solve this the real way. The real way. Maybe the real way is a constraint solver, but it's annoying that this is not like 3 times B. Because that means that this is like kind of unaligned. I think this has to be a constraint solver thing. That's gonna suck to write, but I guess just gotta do it. The number of things we output is definitely equal to the number of times we can divide A by 8. So it's definitely like 8 to this thing. Okay, I do have my Z3 bindings, right? If I don't, I'll be very sad. Oh, I gotta remember how to use Z3. I might be writing this in the REPLs just so I can remember. Boolbear. Bool val. No. Boolean constant. I could use a bit back. Let's use a bit back. Okay. Bit vector constant named this. Maybe the number of bits of a. Oh yeah. So the number of bits here is clearly going to be the length of this times 3, 16 times 3. Okay. So we have this. We have a solver. We do Z3 Python. Okay. I really forget how to use this, so This will have to do. Is there a bitback in here? Yeah, sure, that works. How do we extract something from the bitback? Well, let's go through this one by one. So what's the constraint that we're going to express here? The constraint is BV. Can I index this thing? No. Index bitback. Extract. Interesting. Okay. High and low. I'm really not sure that I'm going to be great at using bitbacks, to be honest, because I don't really know how to do these. Maybe I should just... No, I should use a bitback. Okay. What does extract do? High and low. Trying to understand which bits it's extracting, but 0, 0, 2, 2. Oh, that's how you get one single bit. Okay. So I want to get the bottom 3 bits. So I think this will be from how do I want to do this? Oh, 16 times 3 minus 3 times I plus 1, I think. Extract from here down to here, I think. So this is going to be B at the beginning of this, and then B XOR 1. Can I do this? I really hope so. Seems like it. B XOR 1. And then extract more bits. Let's extract 3 more bits. I really hope you can use this as an argument to extract, and that extract does not require constants. That's not great. Bitback might not be what I want. Dude, I am so rusty with Z3. I could always just do it with a bunch of bool vars and like a really complicated logic, but bools. Maybe I use bool vector. I don't like that. Yeah, fine. I'm like trying to read things in base 3, so I thought bitback might be nice for that, but let's do this. Okay, that's how many bits we have, and then what we're gonna do is we're gonna get bits. Yeah, these bits, I think. So we'll go in order from like high to low, like most significant bit in the left. Cool. So reg B is now going to be 16 times 3 minus 3 times I plus 1. I'm going to rewrite this in a way that's a little more reasonable. 3 times 16 minus I. Okay. And then from here, so this one, 0, 1, or sorry, 1, 2, 4. So 4 times this plus 2 times this. This is like base 2. I'm extracting like 3 different bits to create a number that's a maximum value 7. Did I turn this off? Oh, I'm gonna turn that off. It do not like that. Why does it not like that? This should be -1, right? Yeah. Okay, we got to the end. Reg B looks like, oh, sick. It actually looks reasonable. And now, oh boy, how is leaderboard doing? Filling up slowly. It's a tough question. And now we have register B. What do we want to do? We technically want to XOR this with 1, which is, I think, just going to be, maybe I'll just do this, just like do it explicitly. Okay. Reg C is now going to be, we're going to get a few bits out of A, which is, or sorry, the original A, which is BV. Or no, it's the current A at this point, which means we need to worry about our offset. But that's fine. We were doing that here already anyways. So this is, I should do, I'll just be very careful. I was debating writing a helper for this, but being careful is better, I think. Divide by 2 to the B. No, I shouldn't do that. I should just index. Because what this is doing is just lopping off bits. It's lopping off B bits off of the end, and then taking it. So this is currently, so what we have here is currently the last 3 bits of A. What we actually want is to lop off a few extra bits first. We're indexing it with, the problem is I worry about indexing negative here. Wait, can I even index a bool vector with another variable? I really hope so. Let's find out right now. Oh dear. Doesn't like that. But I probably have this. And it does like that. It better like this. If it doesn't like this, I'll be sad. Oh dear. This needs to be a constant. Why can I not XOR reg B with something else? Can I XOR it with itself? No. Oh, because what I want is a bitwise XOR. Honestly, I should just do 1 times this XOR 1. That only affects this last bit, so I think I just want to negate this. I'm a little nervous about that, but I think it should be okay. And then now let's see, can we index this with reg B? Oh no. Get index bool vector with variable z3 pi. Oh no. Oof, it's gonna be rough, but we'll try it. The annoying thing you can do is you can do just add a bunch of ifs and sum them all up. For what are the possible slices of this? Well, at this point, these are the three values we were slicing. So I think what we care about is reg B can be any number up to 7. So we can at most chop off 7 bits. So we just need to add all possible cases, the like 3 possible cases. Or sorry, the 8 possible cases. And we'll do that by adding a bunch of junk. Okay, the cases here are if reg B equals 0 or equals I, then what is the value we would like to get? The value we'd like to get is this, but indexed. Oh, I shouldn't use I again. If it's equal to j, then what I would like to get is this, except minus j. But there's a catch here, which is if this thing is out of bounds, then I want to handle it properly. No, I hate that. Okay, fine. I have to handle the negative indices explicitly. Bit bool vector at if index is less than 0, then we just return 0. Otherwise, this. Okay, so now this just becomes this. So now we're fine. Fine on that front. You'll see what an ugly expression this looks like later. Ooh, I almost copied that not. That would have been really bad. So this is just, I think it's just that. Now you'll see what reg C looks. No, multiply by be bad. Whoopsies. Don't forget your returns. Okay. If this, then this. Otherwise 0. So it's sort of like one hot encoding reg C here, which is why it will look horrendous. It doesn't even render it. Dear. This might be really awful. Anyways, so now we have reg C. From here, it should be smooth sailing. This step we ignore. This step we just do. XOR with 4. Well, it maybe suffices to recompute this quantity. The bitwise XOR is so annoying. Maybe I should represent reg B as a few different bits. Yeah, fine. We'll do it like this. Nope. So we'll represent reg B separately, and then we'll only turn it into like an integer-like thing when we actually have to. That way, we can do negations as we please. That was also a bug. Wow. Okay, well, a good thing I'm catching all these bugs, I guess. Doesn't really inspire confidence in the rest of my code, but 2 times reg B1 plus 1 times not reg B0. So this gives us the reg B that we use for this step. So that's all good. Then the reg B at the end of this, or honestly, maybe we just, okay, so that's the XOR. Turn into this value. Now we do the XOR 4. XOR 4 is just going to be toggling this bit. Now we do the XOR C. The XOR C is pretty awful. Once again, we want to do this trick, I think. Reg C2, Reg C1, and Reg C0. And then now, these are all going to start off at 0. Oh, but these are Booleans, so that will suck a little. Or reg C2. We'll write it as a big chain of ors. I might regret this later. Fine. And here we do the conditional. If reg B is equal to J, then this one is BV at 3 times 16 minus I minus 1 minus J. Yep. Otherwise, it's false. Okay, reg C1, reg C0. This needs a minus 1, minus J, minus 2, minus J. Okay, I think this is all right. It's a little annoying because at most one of these in the big OR branch can be true, but I'll just not worry about it. C3 is smart. Maybe it'll figure it out. If it doesn't figure it out, then oh well. Then it's back to the drawing board. Oh, I could have done this, I guess, with like a sort of recursive backtracking maybe. Would that have been untractable? I'm not sure. So great. Now we have all the bits of reg C. And hopefully XOR lets us work with bools. That it does. That's nice. Cool. Reg B2, not reg B2. And then reg B2 is XOR of reg B2 and reg C2. Do the same thing. 1 to 1 and 0. Okay, so now we have done this step, and now we're ready to output. So let's add a constraint. And the constraint is that we could turn these into bits. Sure, target B2. Sure, target B2 is going to be T. T is our target thing. T shift 2 and 1. I'm extracting the bits, individual bits, out of this thing. And then we know that reg B2 must be equal to target B2. Reg B1 must be equal to target B1. Reg B0, target B0. And we're good. The solver, how does the solver work again? Cannot type. S equals solver, and I just add constraints. Okay, cool. So I think in that case, and then we'll just do sol dot add our constraints. And then finally, we hope that this works. If it doesn't work, then, okay, what's the problem? Reg B2, target B2. Oh, these need to be bools, I think. Yeah. Just fine. That works, right? Bool of 1, bool of 0. Cool. I don't know why I was doubting that that worked. My brain is a little haywire right now. Supplied sort. Where did we get this from? Oh, this should return not 0 but false. Unsat. No. I hate to see that. Man. There could be, it's impossible to debug this, I think. Just curious, the pressure off yet? Pressure's off now, okay. Wow, we're 44 minutes in? Time flies when you're having fun. Man. Okay, well, I will spend longer on the Z3 approach because in principle, it should be able to work. And we'll start by testing it on something really small that we know. So like if we sim, for instance, we can sim like a number, 1, 2, 3, 4. We see what it outputs. We know that this is solvable. So we'll just ask it about this and see what it says. It says unsat. That's not great. If we sim 5, that outputs 0. Okay. Start with something extremely simple, which is just this. Or sorry, just this. This says sat. Okay. Well, not the most useful. I don't know. It probably doesn't even have the right answer, but let's find out what it gave. I'm trying to remember how to actually find the no, sol.check. Evaluate model. I don't have that many variables. I do. I have a lot of variables. Funny how that works. Or not a lot of variables, but a lot of things happening there. I wonder if I was able to do smart things here. Maybe that was why I was able to solve so fast. But anyways, I think that Z3Pi check value of variables. No. Check solution. I really always forget to do this. This is the thing I'm on. The model. Let's get the model again. And then, oh, I see. We can do this. Can I do this to get the whole bit vector? No. Oh, whoopsies. That probably wasn't helping. I mean, this wasn't really a bug in the first thing, but still sat. Okay, so 4 plus 2, it thinks the check of 6 outputs this, outputs 3. Does it? Sim of 6 outputs 3. Yes, it does. So far, so good. Let's go straight back to this and make sure it doesn't work. Still doesn't work. Yep. Go back to debugging. So now, let's sim something a little more complicated. 2, 5. It still thinks it's sat, and let's make sure its solution is right. Ah, weird. So this is not correct, and yet it satisfies the criterion. So why don't we can evaluate these things as we go. Like in the model, we can check what it thinks these things are. So and now really, it won't evaluate this for me? Oh, maybe I could do hmm. No, that is really not what I wanted. I didn't even look at the answer there. Oh, model.evaluate. Okay, that's progress. Wait, could I have just done this? No, I don't think so. Well, anyways, so let's do this. So here's what we'll do. And then we'll just call this yeah, that seems fine. And then at the end, we do name expression, and then name model. I'm going to change it to model. Model.evaluate expression. Okay, so it thinks reg B is 6 after the first iteration. So I guess also let's do this. Wrong order. I don't like this part. I remember it's always super annoying to try to actually get like a real thing out of this. Is that all I need to do? Somehow I don't believe that. Oh, yeah, that seems fine. Okay, cool. So it thinks with 7, the very first register B is 6. Is that true? Well, it's 7, 7 mod 7 XOR 1 is in fact 6. So it's correct about that. Great. Now, what does it think reg C is? We never really computed reg C explicitly, but that's fine. So when we're done here, reg C2 I really hope I didn't mix up like the endianness of these or something, but it's pretty likely to be honest. Ooh, it thinks C is all false. That's actually correct, I think, right? Because B is something large and A is just like not that big. So it's just going way out of range. So C is correct here, I think. This A step we ignore. And then the thing it outputs, or it thinks that it outputs, is this. I'm going to do this thing again, purely for debug. Thinks the output here is 2. And what was my target? My target is 2, 5. So at least that part is reasonable. Do I think 7 does actually output a 2? That is correct. So the problem comes in the next loop. So it could be the case that my indexing here is just entirely bad. We'll get there. Patience. Okay, so back to this. When we enter the beginning of the next loop, it thinks register B is now 1. That is not possible when it is 7. So something went wrong here. 3 times. So when I is 1, now, yeah, 0, 1, 2 are the indices. Oh, no, wait, sorry, reg B is 1? No, that's actually correct. That is actually correct. Because, although we fail because of the jump not 0. Oh, maybe it's the case that this actually is a valid input if you ignore the jump not 0 bit. It doesn't help me with my unsatness, but we'll get to that. Jump not 0 to the beginning. Also, give me 1 second to make sure that I have enough space on my drive for the video. I'm worried it's getting kind of long. So I'm gonna pause the video and I'll restart in just. Okay, and we're back. I was just deleting some other videos to make sure, or to make space. My drive is running a little low on storage, what with all these videos I'm recording. Okay, so back to this. What's going on here? Yeah, so if we were able to like circumvent the jump not 0, is this doing the right thing? That's a good question. In that case, register B would be 1 after these 2 steps. We are again looking, I think, too far. I think it should just be 0. Reg C is still 0. But because we XOR 1 with 4, we get 5, XOR that with 0, and then we output a 5. Yeah, that actually, okay, it is actually correct. It did give me values that result in the correct output if you ignore the jump not 0 condition. So I think the jump not 0 condition is basically saying that these 3, it's not that these 3 can never be 0, because it's that we can't ever have a prefix of some reasonable length be not. I'm still confused why this doesn't work then. Still unsat. I'm still sad about that. Whatever. The jump not 0 bug is I need another constraint. Another constraint won't make something unsat sat. So there's still another bug that I'm not finding here, but I guess I'll at least fix the first one. So yeah, I think it is the case that the first 3 bits of this cannot be 0. That is all. I think that is sufficient. Yeah, I think that's sufficient. So 1 of these has to be true. Cool, and now it's unsat. That's annoying. I wish I could feed it some example and see what it does. Maybe we can actually give it a list, like literally just give it what I know is the answer. Speaking of which, what is the answer for this target? I don't actually remember. 2, 5, 2, 5, 2, 5, 15, 15. Okay, so the actual answer here is false, false, true, 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 true. And I guess if we just ever add like sol.add false, hopefully this will just raise. Oh, no, it doesn't. Okay, well, it's annoying. Will it even do like... that's not great. Can I simplify this? Simplify. This might just not be possible. But I could do this. I forgot. I could do that, I guess. And just see when it fails. Sure. Why not? Let's do that. First of all, if I just run this, it'll fail for some silly reason like this. Not. Oh, do I need to make them like bool consts? How do I set the value of this? Or is this a variable by default? Unclear to me. So what's the problem here? Problem is that, why is it not like that? A bool ref plus an int. Where's the bool ref coming from? It's coming from this. Yep, that is a bool ref. Can I do this? No. Do I just trace this code extremely carefully? That doesn't feel useful. Wait, is this -1? Is that the correct offset? Did I mess this up really badly? Oh, I bet it's this. Let me think carefully about this, because this was meant to be copied from this initially, I think. Should it just be this? $15. Oh, it's working. It's working. Ah! Does it work? Does it work? Oh, oh, oh! I think it worked. Oh, this is sick. Oh, this is sick. What's A? What's A? There's my answer. The lowest positive initial value. Well, I found a value. I don't know if it's the lowest. Oh, it worked. Oh man. Okay. Oh, that was brutal. Oh man. I think even if I hadn't written this bug, I would not have leaderboarded. So I don't feel that bad about it. I was just really slow, like getting out the Z3, because I did not know what the best approach to do for this was. Yeah, I think so. I'll try and explain a little bit of my thought process. Part one is pretty straightforward. I think it is kind of just implement a complicated looking thing, where you have this really short program, but you interpret these as instructions, you simulate, you have an instruction pointer, you have registers, and you do some stuff. It's certainly complicated, and getting it right and not writing bugs is probably takes some effort. But there's like nothing super advanced going on there, I think. Part 2 then says, so one important mechanic of part 1 is that there's an output instruction, and it will like print output. And part 2 says, now what is so you were initially given a value for register A. This value is a lie, ignore it. You can put in any value you want here and run the program with that. What is the smallest value you need to put in there in order to result in printing out an exact copy of the program? And that's it. So what is actually going on in this program? So my approach to this was understand what's going on in the program and try and like reverse engineer it. And I have a small background in reverse engineering, so this works out pretty well for me. So here's the program, and I decoded it to sort of this pseudocode. And I'll note that before I even did any reverse engineering, I like speculated from all these like modulo 8 values in the instructions, and the fact that this program, like everything here is like 3 bits long. I suspected that it was roughly just taking A and spitting out. So if you look at A's bit representation, if you look at this bit representation and you like chunk it into 3s, what I roughly suspected it was doing was like doing some operation on each chunk and then outputting it, and then dividing by 8 and then continuing this process until it was out. That was like my speculation immediately. It turns out it is kind of doing this, but there's a catch, and the catch is that it doesn't just output. So if it were just outputting each chunk, say like XOR 4, then it would be very easy to like work with each chunk individually. You know that the first chunk should result in outputting a 2, and the next one should result in outputting a 4, and so on. But what's actually happening here is the very first chunk here. So it takes this, and it actually uses the value of this chunk to go look somewhere else randomly into this entire thing. And then it takes those bits and XORs them with this, and then also XORs them with 1 and 4. And because of that, there's like a very non-trivial dependence between separate chunks. It might be the case, let's add this to multiple 3, might be the case that the very first thing that gets outputted here ends up being here. Like we can even go through this example. The very first thing that gets outputted, so A mod 8, this is just taking the last 3 bits. So this XOR 1, so that gives us XOR 1, so it gives us 3. So because B here is 3, that says, okay, go look 3 bits to the left, and that's how you get this C value. The C value is what's used to mess up the thing before outputting it. So we go 3 bits to the left, and we find these 3 bits. I'll note that technically it like grabs the entire thing. It doesn't just grab 3 bits, but it doesn't really matter, because the only way that C gets used is it gets used at this XOR against B, and then we're always outputting B modulo 8. So it suffices to just think about the bottom 3 bits of B and C at this point in time, because XOR is like a bitwise XOR. So that's why we only care about the 3 bits of C. So as it happens, it would extract these 3 bits, which are zeros. Then I'm going to skip over this instruction for a second. So it takes these zeros, takes this B. So B was the thing it initially extracted. Remember, it XORed this with 1, so that resulted in this. This told it to grab this. Oops. And then what do we do? Right, so then we XOR this with 4. 4 is just this bit. So if you're familiar with octal, basically what's going on is, or binary for that matter, this digit has like a value of 4, this is a value of 2, and this is a value of 1. So XORing with 4 is just toggling a single bit in the 4's place. So XOR 4 toggles this bit, so this is the new value B. Then we XOR with this thing. We happen to get all zeros in this case, so it doesn't do anything. but you'll see like in the next iteration, it'll do something non-trivial. So the very first thing that this thing outputs should be 0b111, which is 7. And let's see my answer for the first part. Yep, the first thing it outputted was 7. Then what does it do? So now we can look at this a equals a divide by 8 instruction. This is just, because we're doing the floor division, this is just lopping off the last 3 bits of a. And then we repeat this whole process. So we lop off these last 3 bits. And now what happens in the second iteration? This is going to be a little bit interesting. So now we again take the last 3 bits, we XOR them with 1. So we get this. Now we got to figure out what C is. So we go and do the lookup. And the lookup, so B here is 1. So we're going to look exactly 1 bit to the left. And that gives us these 3 bits. So you'll notice these are not aligned anymore. This is part of what makes this really annoying. So now we know that this is 100, 100 in binary. And so once again, we do this XOR 4, so that changes to this. And then we XOR with C, which is this. So we get this back. So we output a 1 here, and that's the next value. And you sort of get how this process goes. But the whole annoying thing is that it's very possible to end up with something like in the next loop, I don't want to go through this like too rigorously because this will just take forever if I do. But in this next loop, we're going to XOR this with this. Now we're looking 2 to the left, and I guess we're not always going that far back, but we're sort of like doing this bit mixing. Like we're looking at bits other than these 3 at the moment, and because of that, things can be like pretty annoying. In this case, for instance, we'll end up going, or maybe this one. This is a value of 4. It'll be 5 after we do the XOR step. So we'll sort of go 5 bits backwards, and we'll end up taking like this chunk, which is kind of far away from this. And this sort of like non-locality means that we can't really like adjust this without also adjusting the rest of the thing. So this like dependency here makes things really difficult to sort of manually like reverse engineer an input. Great. So now we figured out like I sort of covered like why it's hard to like manually look at this and reverse engineer. Reverse engineering, what it does is fine. Reverse engineering the actual input that gives you this is hard to do because of this step specifically, this like grabbing the bits from other parts of the thing. So what I ended up doing with this, and this is a fairly common thing to do in like reverse engineering in general, is you break out the constraint solver. So Z3 is a theorem prover, is what everyone calls it, but like for our purposes, it is a constraint solver. You can throw in arbitrary expressions and say, hey, please find the variable values that like solve this expression, and it will just do it. And this problem is called SAT. It's the Boolean satisfiability problem. Everything here is ultimately Booleans. Here it's pretty clear because I had like a bool vector, but it can take bit vectors and do sort of arithmetic operations, and secretly they're all bools behind the scene. But this problem is NP hard in general, so it's not possible to solve it efficiently in the general case. But Z3 just has lots of great heuristics, and it really just does a great job of like finding solutions, even when in general you shouldn't be able to like solve the problem in general. Yeah, so basically what I did here is I just wrote all the constraints into Z3 and then said, please solve it, and it solved it for me. And that was the problem. So Z3 is a really powerful tool because of that. The downside is it's very tricky to use. Like you saw how hard it was for me to debug this when I had like a fairly simple just like indexing error. What it does is it'll tell you if the problem is satisfiable or not, like if there exists a solution. And if it says there doesn't exist a solution, then like, what are you meant to do here? It's like pretty hard to debug it. But yeah, the actual constraints here, I'm not really sure anything here is too interesting. I did do some tricks, like the value of B here is technically like an integer between 0 and 7, but it's easier to represent the 3 bits separately. So I just keep the bits separate, and that's easier to work with because I can do the XOR operations with just like knots and keep everything as Boolean variables, or Boolean refs, I guess. The other trick I did was, this step is actually pretty annoying. Like, you want to find certain bools from the bool vector according to some other indeterminate value. That is in general like a tricky operation to express. One way that you can express it, and that I did, is with just a massive chain of if statements. So Z3 can handle ifs just fine. So you can say like, if b is equal to 7, then you get like bits, let's see, shifting 7, so it would be bits 9, 8, 9, 8, 7 of BB. Otherwise, then you chain another if. If B is 6, then you want bits 8, 7, 6 of BB, and you repeat this process, and you end up with this like horribly nested thing that you would think would be extremely intractable to solve. Like, it just seems like, how is Z3 going to do anything remotely useful with this? But it's actually just really good at simplifying things. And yeah, it just kind of works its magic. So that was what I did. That was the trick I did here. I like loop through all possible values of j. It helps that there's only 8 possible values here. If this could be much larger, like 200, then this chain gets really long, and I'm not sure if Z3 can really handle it so well. I think there might be other tricks if that doesn't work. I am not very proficient in Z3. I'm sure someone in my comments is more proficient than I, and I'm sure that they will happily suggest like what I could have done instead here. But like, this is what I did, and it works for this problem. But yeah, so that was one of the other tricks I used. After that, I think it was fairly normal. There wasn't anything too interesting. Yeah, so basically I'm simulating the loop here of the core logic, and then whenever the output statement arrives, I add a constraint that whatever would be outputted, which is these 3 things, must be equal to whatever I need to be outputted. And yeah, that's it. The constraint up here about one of these 3 things being 1 is basically this jump not 0a. If the top 3 things are all 0, then my code incorrectly thinks that it has an extra loop to do stuff, when in reality, what would have happened is a would have been 0 by that point, because we've already like right shifted all the way. If these were zeros, we already would have right shifted all the way such that we're just left with this, and it wouldn't have actually done another loop. So yeah, that's just there to force my code to, or force the constraint solver to realize that it has to have something there if it wants to like do the loop the last time. And yeah, and that is day 17 of Advent of Code. That was a pretty long day. So I ended up doing like not terribly. 271 is still pretty decent. I'm curious if there's something better than a constraint solver here. One thing I thought about was, yeah, so I didn't realize this at the time. Well, this is still a little bit not great. But at the time, I think I thought that the mixing, like when it grabs C, I thought it could grab C from pretty far back. And the fact that it can only actually grab it from up to 7 values to the left means that there still is a decent bit of locality here. And maybe you can kind of like brute force the last few bits a few tries at a time. So maybe you can do some sort of recursive backtracking thing where you like find some possibility for the last few bits that gives you the first output you want, and then you sort of recurse in figuring out what the next few bits are. This seems pretty involved, and I shudder to think what the code would actually look like. It also just might be completely intractable. It might be the case that this just branches far too much, and you can't actually solve it that way. I have no idea. But I'll be interested to look at the Reddit mega thread and sort of see what everyone else has been doing. But yeah, I think that's all I have for day 17 of Advent of Code. So I will see you all tomorrow.